In the LCR lab, you will use a combination of capacitors, resistors, and inductors to make alternating current circuits, and then using Logger Pro, so this cable is connected to Logger Pro, it's the voltage probe, you will look at the signal that you're obtaining in Logger Pro. So it's a fairly simple experiment, it doesn't take very long, but you are going to use a charging discharging thing again, where you're charging the capacitor and then discharging it through the inductor. And in the first part of the experiment, you're not going to use a resistor besides the resistance of the inductor. The inductor has about 600 ohms of resistance, but in the remaining parts of the experiment, you will use a resistor as well. So you will remove the wire, put this one here, and stick a resistor in that place. But for now, we have a simple circuit that only has a capacitor and an inductor. This is a 0.022 microfarad capacitor, and I'm only using one battery. I'm only connected to this one battery. So I will charge the capacitor and discharge it through the inductor, and it doesn't work if you just do it like this one time, pressing the charging and the discharging buttons. So what I often do is just alternate between charging and discharging while waiting for Logger Pro to record the data, and you will see the message waiting for data or something like that on the screen. Just keep on pressing these two buttons. It has to do with the triggering. So depending on how high the capacitor charges and where the triggering is set, the data won't be recorded in Logger Pro unless it hits that particular triggering value. So after you record the data, you will plot, you do some curve fitting, it's outlined in the lab manual, and then you will perform this experiment with another combination of resistors and capacitors. So the inductor stays here. This 0.022 microfarad capacitor will be connected in series to a 1 kilo ohm resistor and then 3 kilo ohm resistor, and then you'll replace the capacitor and use a 0.0047 microfarad capacitor with a 1 kilo ohm resistor and do the same thing. Record the data and then analyze it. In the resonance circuit part of the lab, you will build a circuit with an inductor, capacitor, and resistor. So the values are 0.47 Henry, 0.0047 microfarad capacitor, and then 10 kilo ohm resistor. And you'll see that I added all these wires here to make them basically be in series. Now here we have clips that go to the function generator and to the scope. So one set of these red and black wires go to the scope and one set go to the function generator. Then we will input a signal from the function generator and read it on the scope. So let's first look at the function generator. We want to plug the function generator into output 2 and make sure that we select that. But then we also have to select channel 2 here. And if you press this a few times, you see that the line moves back and forth and you don't know which one it is. So channel 2, it will say here channel 1. Now it says channel 1 waveform, but I'm going to switch it to channel 2. So that's what I want to do, so that the signal is going to be output from the channel 2. So now I'm told to set the frequency to 4 kilohertz. So I have to select frequency. So frequency is selected, and I need 4 kilohertz. So kilohertz is over here. Now I have the frequency selected, and I need the amplitude, so that would be that button over there. And the amplitude is supposed to be 18 volts peak to peak, so 18 volts peak to peak. And the scope did something when I set that up. I'm going to cheat and press the auto button and see the signal on the scope. So I have 4 kilohertz and 17.8 volts peak to peak is what the oscilloscope is reading. So I'm putting this signal from the function generator into my LRC circuit, and the scope is reading exactly what I'm outputting. Now I'm going to have to switch the cables on the Pasco board so that the scope will read something different. So now I have to switch the probe from across the function generator, and now it is recording the signal across the resistor. One thing I would like to draw your attention to is the fact that the ground for both the scope and the function generator stay in the same spot. If you don't keep the ground in the same place, then you can damage the equipment here. Now let's look back at the function generator and the oscilloscope. So we're going to read the signal that comes out of the scope, which is really connected to the LCR circuit here. So I'm going to try to find the resonant frequency. So I'll press frequency here so that I can use the dial over here and change the frequency. And I'm going to do that slowly and watch the signal on the scope. So the resonant frequency is where the amplitude is maximum. So I'm going to turn the frequency up a little bit, and I see that the signal went down. So the amplitude here went down. So I'm going to go back up and up a little bit lower now. So I'm at 3 kilohertz. And did you notice that the amplitude went down a little bit when I went from 3 kilohertz to 2 kilohertz? So going from 2 to 3 increases the amplitude. The amplitude stays about the same until about 4 kilohertz, and then at 5 kilohertz the amplitude goes down again. So very coarsely here, I figured out that the resonant frequency is somewhere around 3.5 maybe kilohertz. I don't know the precise value. So at this point I can just use the keypad and enter different values for the frequency and then measure the amplitude on the oscilloscope. So you'll have to take data points and then plot them frequency versus amplitude so that you can see, you can find the resonant frequency. Now once you have data for frequency versus amplitude, you will plot that in origin and you'll get a nice curve that you will have to fit a Lorentzian to, and that will give you the value that you're looking for.